pleasure to be here contributing to this fascinating day of talks. All the more so because it's International Year of Light, so this celebrates a number of significant anniversaries relevant to general relativity, not least the centenary of GR itself, but also 150 years since the seminal work of James Clerk Maxwell on electromagnetic waves, which paved the way for relativity. And moreover, it's 50 years since the first discovery of the cosmic microwave background radiation. So International Year of Light is a backdrop to many of the events that I have been contributing to and indeed helping to run in Glasgow this year. We have a Festival of Light coming up in a few weeks' time to mark James Clerk Maxwell's birthday and a series of lectures associated with these broad themes. Einstein is also a character that's figured prominently in my history. I didn't quite teach myself general relativity. I'm hugely impressed that Pedro did, but I did have an excellent tutor as an undergraduate, and it's of course I think true to say that it's only by teaching a subject like general relativity that you begin to edge towards perhaps understanding it. I'm reminded of another of Einstein's great quotations where he says he never teaches anyone, he just creates the conditions in which they learn for themselves. So I'm going to try and do a little bit of that today. It's clearly a big field to cover in only 40 minutes, but I mainly just want to give you a flavour of what gravitational waves are, and most importantly, what astrophysics we might hope to learn by their detection, by their direct detection, from, in the first instance, a ground-based network of what we call laser interferometers. So more on that in a few minutes. And then I'll also talk briefly, if there's time, about future plans for a space satellite, and indeed a set of satellites, which Pedro briefly alluded to, 3 satellites collectively known as LISA, which it now looks like may not fly until something like 2035, but this would broaden and widen yet further the gravitational wave spectrum. I was struck by something Pedro said in setting the context of the discovery of general relativity and how he referred to Einstein as going on to become a great celebrity. I suppose in some ways he was the archetypal celebrity scientist long before we had Stephen Hawking or, dare I say, Brian Cox. And what you see in 1999 is that the magazine Time actually voted Albert Einstein the person of the 20th century, not the scientist of the 20th century, but the person of the 20th century. That was an editorial board decision. There was a public vote as well, and the public actually voted for Elvis Presley. Decide for yourself who got that one right. But he is undoubtedly an archetypal celebrity scientist in the sense that I actually have an Einstein action figure on my desk back in Glasgow. But of course, we're not here to deify him as a celebrity. We're here to try to understand a bit about what he actually tells us about the universe through this wonderful, beautiful theory of general relativity. So, the previous speakers have set the scene for this wonderfully. They've even referred to John Wheeler. Pedro was setting the scene there as to how the renaissance of general relativity was driven by characters like him and Dennis Sciama. And John Wheeler, I believe, is the person to whom this great quotation is attributed. So this alludes to, albeit rather hackneyed, as Pedro said, I think quite valuable metaphor that we use for the bending of space-time by the presence of matter and energy. We think of a stretched sheet of rubber into which a massive object is dropped, and space-time tells matter how to move, and matter tells space-time how to curve. So if we're thinking of gravitational waves, what we really must now do as well, and this links to something Pedro was saying in answer to the questions that Mike asked at the end, is to think of space-time not as a static warped sheet of rubber, but actually as a dynamic entity in its own right. In other words, think of it like a trampoline, which means if you drop a heavy object into a trampoline, then of course the motion of the object will be affected, but the trampoline itself will be too. The trampoline will vibrate, it will wobble. So the ripples in space-time that we refer to as gravitational waves, you can think of loosely as analogous to the wobbling of that trampoline. Now, how do we detect them? Well, those ripples are going to spread out through the universe, and as we'll see in just a few moments, our principal efforts to detect them in terms of the ground-based instruments that I'm mainly going to describe are to do with detecting the disturbances that those ripples produce when they reach the Earth. And that's the first difficulty we have in detecting gravitational waves. I think Michael was waving his hand and saying, we are changing the curvature of space-time, but by an incredibly minute amount. Firstly, because the mass of my hand is not very great, and secondly, because I can't move it close to the speed of light. So we really have to look for objects out there in the universe which are much more massive, much denser, and moving close to the speed of light to produce appreciable ripples in space-time. And that means we're looking for violent events. We're looking for events like exploding stars, core collapse supernovae, different from the type 1a supernovae that Michel Furlong referred to, but nonetheless cataclysmic events at the end of a star's main sequence lifetime. We're looking for collisions of stars, like neutron stars, the end product of such a core collapse supernova, or indeed black holes, the end product of even more massive stars, and perhaps even from the Big Bang itself. Well, we certainly do expect there to be gravitational waves from the Big Bang. We heard about that a little from Pedro and then also from Hiranga. And while, if time permits me, I'll try and say a little bit about the prospects for detecting primordial gravitational waves from the CMBR, which has been largely covered by the previous speakers, and in particular, as you know, Pedro began with reference to that very exciting event in early 2014, when we thought, just maybe, we were on the brink of such a discovery. So let me say from the outset that because of the limitations of time, I'm mainly going to be talking not about gravitational waves produced in the Big Bang, but instead gravitational waves produced by astrophysical sources in what you can think of as our local patch of the universe. Albeit local is a relative term here, we're still talking distances of millions or hundreds of millions of light years. But we're trying to detect gravitational waves from those comparatively local events as they wash over the Earth. So, do such gravitational waves exist from astrophysical objects? Well, we're pretty confident they do, because we have indirect evidence in a variety of forms that's really rather conclusive. There's a binary pulsar system. That means it contains two neutron stars, one of which is rapidly rotating and producing rapid pulses of radio waves, which are just shown in cartoon form here, like a lighthouse beam, as the object sweeps across our line of sight. And binary pulsar systems like this one have been studied, in this case, for decades, in other cases for not quite so long. But this really seminal set of observations by Russell Hulse and Joe Taylor, taken with the radio telescope in Arecibo in Puerto Rico, have led us to be able to test a number of the key predictions of Einstein's general relativity in relation to systems like these. In particular, the orbit of that binary pulsar system is evolving. And we believe that that's because the two neutron stars are getting closer together. And that's consistent with Einstein's prediction that such a system should be radiating away energy in the form of gravitational waves. But right now, that binary pulsar system and others like it that we've detected in radio waves, we aren't sensitive to the gravitational waves from those systems because they're too weak in amplitude and they're too low in frequency. What we're looking for is a system where the binary neutron stars are much closer together, and therefore the gravitational waves that they're producing are higher in amplitude and higher in frequency. And that means instead of simply being able to indirectly see evidence for them through the effect they have on the binary neutron star orbit, what one might hope to do is to more directly detect evidence for those gravitational waves by detecting the disturbance that they produce as the waves pass through our solar system. But the very fact that this binary pulsar system exists gives us perhaps some more confidence that other systems rather like it should exist and should indeed be much closer together, their orbits much tighter and closer to the point when the two neutron stars will merge. So in cartoon form, this is the sort of thing we're looking for. Now, of course, if the gravitational waves produced were of that amplitude, we would have found them a long time ago. This is just a cartoon representation to give us a flavour of the sort of effect we're looking for, the spreading out of those ripples across space and time. Now, because typically these sources will be rather far away, and because the amplitude of the gravitational waves declines with distance, then it means that by the time those ripples reach the Earth, just like ripples spreading in a pond, they're incredibly weak. In fact, the headline figure is that to detect them, we need to measure movements less than 1,000th the size of even a proton, about a millionth the width of a human hair. Now that sounds unimaginably challenging from an engineering and technology point of view. But that's what I'm going to try to describe in the next half hour or so. So, how do we do it? Well, let me cut to the chase and let me talk first about what we already have operating. We have a network of laser interferometers. So I'm part of the LIGO collaboration, Laser Interferometer Gravitational Wave Observatory. I'm not here speaking officially on behalf of the collaboration. We have a spokesperson for that, and that's the person I'm sure you'll hear from as and when a discovery is made. But I do have a particular responsibility within the collaboration. I'm one of the co-chairs of our Education and Public Outreach Working Group. And that means I've taken particular attention on questions like, well, how do we describe the technology? How do we describe the science goals? How do we describe the anticipated discoveries to a broader audience? So hopefully the benefits of that will be apparent to you as I describe this. But it is challenging because the technology is not something you need every day. And of course, it's not even like a conventional astronomical optical telescope where one can just show an image of what one would see as you switch that telescope on. In that sense, these instruments don't really see the universe. Maybe a closer analogy is to think of them as hearing the universe. We'll get back to that in a few minutes. Anyway, where they're located is in Livingston, Louisiana, and Hanford, Washington State. And these are big instruments. So how's it all done? Well, at the risk of sounding like one of those Las Vegas magic shows, it's all done with mirrors and lasers. And it goes back, ironically, to a basic piece of physics apparatus which was pioneered by Albert Michelson around the time when Einstein's special relativity was still very much being put to the test. It was a few years before that Albert Michelson conducted his classic experiment that we come to refer to as him using a Michelson interferometer. Now that might not be a phrase that everyone in the room is very accustomed to, but it's actually something which many first-year physics students might meet in the laboratory. It's your physics lab courses, first-year physics lab courses, we'll get them playing with. I did notice a few years ago, though, that the whiskey company Bunnahabhain, based in the island of Islay in Scotland, they had an advertising campaign called Great Unpronounceables of Our Time. You probably agree that Bunnahabhain certainly fits that description. So they had a Michelson interferometer as one such example of a great unpronounceable. But as I said, to a physicist, this is actually part of our sort of standard toolbox with which we try to teach physics and try to understand optical phenomena. So what is a Michelson interferometer? So here's very much the scaled down version. You take a light source, these days a laser, split it into two beams. One beam goes one way, one goes the other. You bounce it off mirrors, recombine the beams, and have a look at what you get. And the basic idea is that if a gravitational wave goes past, then what we expect that Michelson interferometer to do is to undergo a periodic variation, hugely smaller than what you see in the cartoon, but along these lines, where basically the arm lengths are periodically stretching and squeezing. So what gives it the name interferometer is that what we're then going to do is we're going to look at the output light signals from the two perpendicular paths and see whether there's a change in the interference pattern between them, reflecting changes in the path length that the light has travelled along. Now you can get constructive, where the two beams are out of phase with each other, or you can get destructive interference where they're out of phase, or constructive where they're in phase. So that's the reason why it's called an interferometer. And we expect movements in the arm lengths which are incredibly small, 10 to the minus 18 meters. That's, as I said, 1,000th the diameter of a proton, even over 4 kilometers. Now, there's all sorts of sources of noise, terrestrial, local to the detectors, which are going to completely swamp that signal. So in fact, remember I said a moment ago that we don't use gravitational wave detectors the way you would an optical telescope, where you switch it on and there's your image, there's a picture of a star or a galaxy. Well, even with an optical telescope, if you're looking at a very faint object, then sometimes you have to work rather hard to process the image and extract the image of the object you're studying from the noise. And that's absolutely the case here. There's all sorts of sources of noise which dominate over the signals we're trying to detect. So this is a rather complicated looking diagram. Let me not focus too much on the details, but just draw your attention to the fact that these different sources of noise, in a sense, compete with each other. And that there will be certain ranges of frequency of gravitational wave where you have a reasonable chance of making a detection, but there'll be other frequencies where you haven't got a cat's chance of detecting anything because the noise sources on the surface of the Earth are just too great. So what are these noise sources? There's things like the photon shock noise. That means you're interested in detecting the intensity of the two laser beams that have gone off in their perpendicular paths. And there'll be variations in that intensity anyway, just because of random fluctuations in the number of photons in the laser beam. So are those variations truly coming from a gravitational wave source, changing the path length and hence the interference, or are they just random fluctuations in the photon beams? That's going to be a big source of noise. And then you've got radiation pressure, the fact that the photons carry momentum, so pushing the mirror, and even by a tiny amount, that could affect your ability to detect a signal as well. And there's others more to do with the surrounding environment and how seismically stable that is. Bottom line is, this is a big, big challenge. So all of them point to long arm lengths. The longer the arm length is, then the better chance you have of detecting a fractional change in that arm length. The LIGO instruments, the arm lengths are 4 kilometers long, and their laser beams pass back and forth hundreds of times along those arms. So the combined arm length is much, much longer still. And inside, what you've got is a very complex array of optical instrumentation. Now, I don't work in that field. I'm a data analyst, and in fact, really, my background's in cosmology, and I'm much more interested in the years that lie ahead that we'll get onto in just a moment when we look at what we'll learn once we begin detecting gravitational waves. But I am hugely in awe of the effort of the instrumentation guys who've put all of this kit together. And a lot of the time, that isn't just to do with optics and material science, but to do with things like making sure there's a vacuum inside the laser tube, because even the buffeting of molecules in the air would be enough to swamp your signal. So in fact, the LIGO instruments have about 1/1000th of an atmosphere of vacuum inside the tubes. So, why build two? Well, it's not a sort of buy one, get one free, alas, but these are expensive instruments of order, $1 billion. Although it has been pointed out to me that over the lifetime of the project, that sort of constitutes about 1 beer per adult of the US population. That doesn't sound too big a price to pay, but maybe that's something we can discuss a bit in the panel discussion. Big science like this is expensive, but the reason we've got two is not, as I said, just buy one, get one free. It's because gravitational waves coming from some putative source, they'll arrive at an ever so slightly different time at the two detectors, and that gives you an ability to locate them on the sky. And indeed, we've actually got a wider global network of gravitational wave detectors. Some of the technology was first tested in a UK-German instrument called GEO 600 with only 600-meter arms, and that technology is now being transferred into the LIGO instruments. I'll come back to that in just a moment. And then there's a Virgo collaboration. They're based in Italy, and their interferometer are 3 kilometers long, the arms. And then there's an instrument called CADRA, building on earlier prototype work done. The collaboration was called TAMA and then CLEO, which is in Japan. So, the LIGO scientific collaboration is more than 900 scientists worldwide. They work on all sorts of different aspects of this. It's a bit like the Large Hadron Collider. I noticed just the other day that they've now published a paper where they've passed 5,000 authors in the paper. Well, we're not quite on that scale, but close. And frankly, a lot of my co-authors, I wouldn't go past them in the street and I wouldn't know who they are. I am accustomed to hearing them a lot on telecons, often at rather unsociable hours, because as you can see, we're scattered all around the globe. But it's been a very impressive amalgamation of experience and expertise across the full range, everything from instrumentation to data analysis and theory. So what can gravitational waves tell us about the universe? In the second half, that's what I want to focus on. Well, the sorts of sources, we've touched on this already, are very violent cosmic events. Things like coalescing binary systems of neutron stars or black holes. The next talk from Marika will talk a bit more about black hole and physics and what we can learn about the more fundamental questions of the natures of space-time, I think. But in a sense, we're using them just as something that produces gravitational waves, which means that there'll be a mixture of wanting to understand the sources themselves, but also wanting to understand objects that interact with the gravitational waves between us and them. Now, actually, not very much interacts with gravitational waves, but one of my particular areas of interest is using gravitational wave sources as probes of cosmology, probes of dark matter and dark energy. Again, if there's time, I'll maybe say a little about that. I've already mentioned that I'm not really going to cover this one, the cosmic gravitational wave background, because at least the ground-based interferometers are not dramatic there, anything too dramatic there. But there's also the possibility of detecting gravitational waves from isolated neutron stars where if there's a little bump on the surface of the neutron star, then that will make it asymmetric, and hence it will produce gravitational waves. And then there's other sources that maybe we don't even know exist yet. So it's always important to leave some room for the unknown, although it's a little bit harder to persuade funding agencies to give you $1 billion to find something that we don't know about yet. So a lot of the effort has focused on known sources and what we could learn about them. So I'm not going to read all through this. This is just to give you a flavour of the fact that in gravitational wave astronomy, like other areas of the electromagnetic spectrum, all the way from radio to gamma rays and X-rays, the goal here is really just to harness gravitational waves as another new way of looking at the universe. These are not electromagnetic waves, but we hope that just like the whole electromagnetic spectrum has led to many dramatic discoveries about high-energy astrophysics, then gravitational waves we hope will lead to similar insights. So, again, maybe this will give you some food for thought for things that you might want to ask questions about in the panel session. But I should mention that in addition to broader astrophysics questions, it is hoped that gravitational wave astronomy might shed some light, no pun intended, of course it's not light, but shed some insight on questions to do with fundamental physics and the nature of space and time themselves, and indeed, as I mentioned a moment ago, cosmology. So let me just say a brief word about the cosmology applications. And this is the only slide where I've got anything resembling an equation on. And again, don't focus on the detail of the equation. H is the amplitude of the gravitational wave, so I've just represented that in cartoon form instead. And we'll come back to another way of representing it in sound in just a few minutes. DL here is what we call the luminosity distance. It's the distance to the source. And the curly M is to do with the masses of the bodies which are producing the gravitational wave. So the bottom line is that what we want to be able to do is by looking for signals like this and using Einstein's general relativity to predict what the signal should look like, to be able to effectively measure the distance of those gravitational wave sources. We've come to refer to them as standard sirens, so it's like an analogy to the standard candle that we heard Michelle talk about before the break. And here we are. There is an audio representation of that waveform you saw in the previous slide. It's what we call a chirp. And if you want to play around with this a bit, our colleagues in Cardiff came up with a nice way to illustrate it. It's a game, an online game called Black Hole Hunter. So what you can do is listen to those sounds, but of course it won't be like that. It will be embedded in noise. And just like Hiranya gave you an audio representation of the CMBR noise, well, our noise from the gravitational wave detectors similarly can be rendered as audio, but it will swamp the signals like that. So our data analysis methods are all about trying to extract very, very weak signals from very noisy data. So, what have we learned so far? Well, we haven't detected any gravitational waves. If we had, I'm sure you would have heard about it in New Scientist, if nowhere else. And, well, we've nonetheless put some interesting limits on astrophysics through the absence of gravitational waves. For example, there was an episode of QI a few series ago where they talked about what the roundest thing in the universe was, and the answer was a neutron star, because the absence of any gravitational wave signals from certain rotating pulsars, rotating neutron stars, in fact, two you may have heard of. One is associated with the Crab Nebula, which is the remnant of a supernova explosion that happened nearly 1,000 years ago. And the absence of gravitational waves from those sources essentially lets us put limits on how different from spherical those neutron stars can be. If they had a bigger bump on their surface, a bigger mountain on their surface, then we should have been able to detect gravitational waves already. The fact that we haven't tells us something. There's another example. This is the Andromeda Galaxy, our near neighbour in the universe, about 2.5 million light years away. And a few years ago, there was a source of gamma rays detected in the sky. This is data from the Interplanetary Network of high-energy satellites, sensitive to high-energy photons. And this box here, rather tantalizingly, overlaps with the Andromeda Galaxy. Now, the expectation was that the source was much further away than the Andromeda Galaxy. But the interesting corollary is that if it really were in the Andromeda Galaxy a source of gamma rays, then there's a good chance it should have been producing gravitational waves, and our LIGO instrument should have been able to detect them. The fact that we didn't essentially predicts expected that this was much further away, which again is more or less what we expected. And I'm reminded perhaps of the Sherlock Holmes story, The Silver Blaze, the curious incident of the dog in the night time, where Sherlock Holmes makes a useful deduction from the fact that the dog didn't bark. But of course, we don't want to make do with non-detections. We want to start finding some barking dogs. And interestingly, a few years ago, we, in some sense, did. There's an event that we refer to now as the Big Dog event, which appeared to be in the constellation, the direction of Canis Major on the sky. And this is an example of where our collaboration has been rather sneaky, but for a very positive reason. In the last few years of the initial science runs of the detectors, what the collaboration undertook to do was to embed in the data artificial signals, but not tell anyone. Only a few people in the upper echelons of the collaboration knew about this. And that was essentially a way of stress testing our analysis methods to make sure that we could actually find something if it's really there. So this did indeed turn out to be a false alarm. It was a very strong signal. Had it been a real signal, it would have been something we would have only expected to happen about once every 7,000 years. But it did turn out to be a blind injection. In other words, we went to the collaboration meeting in March 2011, we opened the envelope like the Oscars, and sure enough, it was revealed that it had just been injected by the collaboration. And on the one hand, we were a bit disappointed, but also very pleased that at least our data analysis algorithms had actually found something. Moreover, we'd also used that as a way to stress test other important aspects of how it's really going to work in the future, which is that we contacted lots of ground-based optical telescopes, and indeed even colleagues operating in the X-ray and higher energies with SWIFT and radio with LOFAR, telling them where we thought this putative gravitational wave signal was so that they could go look for an electromagnetic counterpart. Now, of course, we didn't find anything because it was a fake signal anyway, but that let us set up some of those procedures and memoranda of understanding between the gravitational wave community and the optical and broader EM communities. Those will be important later. So what's been happening since those initial runs? We're now moving towards advanced LIGO, and I'm moving towards the end of my talk, so I'm going to get a wiggle on here. So for the last few years, LIGO has been upgraded to become advanced LIGO, and the goal is to increase its sensitivity by at least a factor of 10, and the installation actually is no longer in progress. I should have updated that slide because it's now being completed, and the science runs will start later this year. There's a number of features which have been built in. I won't dwell on this, but again, we'd be happy to discuss over coffee some of the details. More powerful moving the size of the cancellation, and also using heavier test masses which are less adversely affected by some of the noises that would mimic gravitational wave signals but aren't the real thing. So the installation work's been carried out by a number of my colleagues who we get to dress in the spacesuits and spend time in this fantastic environment where all this high technology has been put into practice. And these new test masses have been suspended, and we're basically kind of almost good to go. This is the sensitivity curve, so hot off the press from just a few days ago, 15th of May, and this is the Hanford Washington State detector and the LIGO Livingston one. And what this is saying, based on the sensitivity we now have, and based on where we might expect the signals to be coming from, like binary neutron stars, how far away could we now reasonably expect to detect a binary neutron star? And we're now getting on, well, in fact, if you combine the data streams beyond 100 megaparsecs, that's about 300 million light years. Now, what's all this scratchy stuff here? These are to do with the normal modes of oscillation of all of those suspended test masses, which means that in certain key frequencies, you'll be completely dominated by noise, but what the precision of the instrument is helping us achieve is to combine those noise-dominated regions to very, very narrow frequency ranges. So obviously, if nature is unkind and gives us a real source at that frequency, then we're not going to see anything. But the sources will evolve in frequency, they will change as they proceed through an event. So in fact, it's not as bad a problem as it may look at first glance. Right, so where are we? Just a few days ago, the Advanced LIGO gravitational wave detectors were officially inaugurated, and the first science runs will begin later this year. You can read much more about this in our LIGO magazine. In fact, one of my rather off-the-wall contributions to the LIGO magazine, as well as writing a few science articles, was to contribute LIGOku puzzles, where we replace numbers with gravitational wave symbols. So if you fancy having both those. The latest edition specifically talks about getting the detectors to design sensitivity, and is a very good snapshot of the huge engineering effort that lies behind all of this. So where we hope to be in about a year's time is to have advanced Virgo online as well. And that means that we will be sensitive to a much larger volume of space than just what LIGO was sensitive to. Now, that basically means that we'll be in a position, if something goes boom, to detect gravitational waves. Now, where will that be? When will that be? Of course, there we're relying on nature to cooperate. So the kind of work that I've been more involved in is not the design and building, but trying to predict what the astrophysical rates will be. So here's a paper from a few years ago, which is probably still our kind of state-of-the-art prediction, and that's saying that really by about 2017-18, the ranges will be high enough that based on how many sources we expect within those volumes, then the number of binary neutron star detections, okay, it could be less than 1, that's the pessimistic end of the range, but it could be as many as 100 per year. So what we've tried to do is to be very honest about what assumptions we're reliant on and give a pessimistic, realistic, and optimistic range. If you want me to give a date specifically, well, 2 years ago we had a meeting in Warsaw where someone asked exactly that question, so a bunch of us sort of had to think, and we came up with January 1st, 2017. Although I did point out there wouldn't be many people at Glasgow working that day. Looking just a bit further ahead as we move to wrap up, LIGO India is well on its way to being officially sanctioned. The Indian government is hugely in favour of taking some of the hardware, which the NSF is funding in the US, but putting it in a detector in India instead. Timescale for that's another few years. But the reason that will be important, again, don't worry too much about the details, but these are simulations of the area on the sky where we might expect a gravitational wave network of detectors to localize the source. And clearly, if you want to phone up your friends in optical observatories and say, we think there's a source over there, if you give them an area of a few hundred square degrees, that's not as good as giving them an area of a few tens of square degrees. So LIGO India is going to help with that. You can see how much smaller the expected error boxes on the sky will be. And that's why it's so important at this stage to start forming those connections with the rest of the astronomy community. And indeed, I'm just back from a workshop where we've been looking further ahead to what might come after advanced LIGO. We call it the Einstein telescope, but again, probably not going to happen before 2030, 2035, but the planning, some of the planning at least, has to start now. And that workshop was in fact in China, because we're trying to get them interested in joining this great endeavour as well. So we just got a recent paper on looking at where would be the optimal location to add additional detectors to the network. That's just out in classical and quantum gravity. So there's lots of information out there. I want to leave myself just a couple of minutes at the end to say something about space gravitational wave detection. But in terms of the ground, there's all sorts of info you can find on our LIGO.org website. So let me just flash these up. The main thing is get the web address in your head and you can go look. You can follow us on Twitter, on Facebook. We've also got a travelling exhibition on gravitational waves, which I'm afraid hasn't made it to Europe yet, but has been seen by nearly 1 million people in the US. And so that's been an interesting part of the project too. And indeed, we've got some movies on our website as we build up towards what we hope will be those first detections in the next few years' time. We've done a Reddit Ask Me Anything session, which was great fun as well. So, as I said, final couple of minutes, let me just briefly say something about other parts of the gravitational wave spectrum. Everything I've talked about up until now really has been up at this end. It's been up at the hundreds or thousands of hertz. If you go to longer wavelengths and lower frequency, then the most exciting prospect really for astrophysics will recently ELISA, the extended LISA mission. I wish there were more I could say